Today's training session is our final session, number 6 of our Block 2 Crew Academy. Today we'll hear about cases of wastewater management and reuse, focusing on small-scale decentralized systems. We have a very good sample of case studies showing very successful results in treatment and reuse in small communities, and I hope you will benefit from this last session. As you all know, this is offered by Crew Plus Academy, which is a free platform established by Crew Plus Project. And this is a collaborative project funded by GEF. And as you know, it's co-implemented by the IDB, the Inter-American Development Bank, and the United Nations Environment Program, and executed by GIZ, as well as by UNEP and the OAS. As we did last week, we asked you to participate in those 2 surveys. The first one, right now at the beginning of the session, and that can be seen on your screen now, is used for registration purposes. So please fill that out so that you'll be fully registered to to today's sessions. I'll give a minute or so for you to fill out the survey, and then we'll continue. All right, so the second survey, as you know, is the evaluation survey that comes at the end, and that will be required for full registration into this. So we are all set. We have a very busy morning today. Our facilitator, Gustavo Heredia Dieters, who you already know very well, is well prepared with a few cases. And he's going to close this 6th session with a very applicable approach to all the material, the technical material that we've reviewed in the past 5 sessions. At the end of the session, after the Q&A, we will welcome Chris Corbin, who's the head of our secretariat for the Cartagena Convention, for some final remarks and the formal closure of our Block 2 Academy. Okay, so without further ado, and due to time pressures now, we move on with Gustavo. Please, Gustavo, the floor is yours, and all the best of lucks.
Thank you, David. Happy to be here for the 6th and last session of this course. Today we will look at several cases. I will present the 2 first cases you see on the screen. One is from Nicaragua, the second one is from Haiti. And then we have 2 guests for the 3rd and 4th cases. First, one case from Nicaragua that will be presented by Selene from Borda. And finally, a very interesting case from Barbados, which will be presented by Mr. Anthony Headley. And actually, he's got a couple of cases within this presentation in the framework of the development of a national water resource policy system. So, right, let's go for the first 2 cases with me. The first one is from Nicaragua, Villa Bosco Monje. This is a pilot project that took place in the peri-urban areas of Masaya City in Nicaragua back in year 1996. I like this case a lot because since this pilot project was funded by the Austrian Development Corporation, it was pretty much like an experimental pilot project. So it was very, very well documented and systematized, and they have all the monitoring of the effluent, and they did different experiments and measurements with the reuse phase and trying out different crops. So we will learn some very interesting details about this case. The challenge here for this project was to implement a wastewater treatment and reuse treatment system for agricultural irrigation. The initial investment was around $42,000, and the capacity is for 1,000 people, so about 100 cubic meters per day. The total area that was needed for this type of treatment was 1,400 square meters. And you can see a picture there in which you can see the constructed wetlands in the center part of the picture. And we will talk about the constructed wetlands and how they work in more detail in the following slides. So the treatment train for this treatment plant, as you can see on the screen, first we have the water works at the inlet, basically a grid and for separating large solids. Then we have a grid chamber. And very important, we will look at this into more detail later, a device to measure the inflow of the treatment plant. Then the sedimentation tank, in this case, it was an Imhoff tank, and we will look at it in more details also. In parallel, we separate the sludge that is sedimented in the Imhoff tank and also the green chamber, and this goes into the sludge drying beds. After the primary treatment, after the Imhoff tank, then we have 4 constructed wetlands in parallel. And the idea behind this was to have 4 units in parallel to try different plants within the constructed wetland and evaluate the differences. And also to have more resilience in case one of the biofilters got clogged, then you have others to move the water through. So let's look into more detail to the inlet works. We have the fixed grid and manual cleaning. As you can see in the picture, you can use a rake for this to manually remove any objects that might be clogging the inlet work. So very, very important to have this pre-treatment step, because otherwise all the waste and plastics and debris would go into the plant, into the wetlands, and creating further problems. So it's very important to separate all these solids at the inlet of the plant, so we end up treating wastewater, not solid waste. This is very important regardless of the size of the plant. Either large or small plants, you need to a way of separating any solids at the inlet. Then we have the grid chamber, in this case a rectangular grid chamber, also with manual cleaning. So we have every sand material that would settle in a very short period of time will settle here, and it won't go through the Imhoff or the wetland. So the idea is that all heavy particles should be separated at the grid chamber. And as I mentioned before, very important to have some type of device to measure the flow of wastewater coming into the treatment plant, because if we don't have means for measuring the flow, then we will be operating the plant without knowing how much water we're treating, right? So if we want to determine the efficiency of the plant, for example, the first measure we need is the flow measurement. We need an idea. We need to have an idea of how many cubic meters per day we're getting. So when you have a channel, you can use a partial channel in order to measure the flow, or a small veer. Or if you go more sophisticated, especially in larger plants, you can have an ultrasonic device to measure the level of the water at your inlet pipe or your inlet canal to measure the flow. But it's very important to measure and register the flow. Then we have the primary treatment, in this case an Imhoff tank. Imhoff tanks have been used for many years. Very well established technology, very robust. In this case, the hydraulic retention time of this Imhoff tank is 2 hours. Hydraulic retention time means that In the average, water stays into the tank for 2 hours. It's not a batch process, of course, it's a continuous process, but one drop of water going into the tank will get out of the tank 2 hours later on average, right? Because the flow also varies along the day or along the week. But especially when we work with anaerobic reactors, this hydraulic retention time is very important in order to give the bacteria enough time to digest the wastewater. So in a septic tank, for example, the time will be less. Then we have the EHOF tank with about 2 hours, and then for anaerobic upflow sludge blanket reactor, such as UASB reactor, for example, then we might need between 6 and 8 hours retention time. So it varies according to the technology and the specific design, but that's a very important parameter for designing any anaerobic reactor. Also, it's related to the temperature. The colder the temperatures, the longer the retention time should be, and the higher the temperatures, you need less time, less retention time in the tank. So in places with tropical climate, you can save on the total volume because you will need less retention time as compared with the colder places. In this case, in this project, there's also on-site sludging, drying beds for sludge. So here we can see on the other slide, all the sludge that gets settled in the bottom of the IMHOF tank can be taken out and taken to the sludge drying beds, in which you basically dehydrate the sludge. The liquid that comes out of the sludge can go back to the treatment plant, and once the sludge is dried, you can use it as a soil improvement also for agriculture. On the picture on the right, you can see a detail of the IMHOF tank. These baffles here are designed so all the scum and biogas goes to the sides, and the clarified effluent goes to the center chamber. That way we're separating the solids in the bottom. Any fat, grease, scum will go up here to the sides. Those sides are covered here by this yellow lid. And in the center, we have the clarified effluent that will go to the next step, which is the secondary treatment. In this case, a horizontal flow, a subsurface horizontal flow constructed wetland. This means that in this type of wetland, the water will flow along the wetland and underneath the surface. So that's what we call subsurface horizontal flow. This is different from the vertical flow wetland. In the vertical flow wetland, we have a set of pipes on top of the wetland, and those pipes distribute the water, and the water will trickle down all the way down. In this case, this is a horizontal flow wetland, so water goes into one extreme of the wetland and will go out to the other extreme. You can walk within this wetland amongst the plants, and the pebbles here, the gravel will be totally dry because the water level is usually between 15 or 20 centimeters below the surface. So you can just walk on top of the wetland and everything will be dry. There's no odors, there's no mosquitoes because there's no exposed wastewater to the environment. At the inlet of the gravel filter, we have a coarser gravel in order to ensure a proper distribution of the water using the full width of the constructed wetland. Then we have smaller gravel through the wetland, and at the outlet we go back to coarser, larger diameter gravel in order to ensure a good collection of the wastewater, of the treated wastewater in this case, at the end of the wetland. And this pipe goes up in order to regulate the water level of the wetland. So if I was to cut this pipe down here, or to the half of this pipe length, then the whole the water level of the wetland would go down. If I raise up this pipe a little bit, then the level will go up. And in the bottom of the wetland, of course, you have some kind of liner. It can be natural or it can be polyethylene sheet, in order to prevent water from percolating into the ground. So that's basically the wetland. In this case, they did use plants. You can also have an unplanted gravel filter. In this case, we have plants, and they have used 4 different types of plants just to try different species. You have all the names there, but basically the first one is common reed, second one is elephant grass, cattail, the third one, in Spanish we call it totora, very common in many places, and the last one, gardener's garters. So all these plants you can find in natural wetlands. So what you do basically is to harvest some of these plants from a natural wetland, and you plant it into the constructed wetland. And then these plants develop a network of roots around the gravel, and the gravel becomes a much more efficient biofilter when it's working with and along the roots of all these plants. Also, what the plants do is they get oxygen from the air, and that oxygen gets injected to the roots. So that is good for the environment of the wetland, so it's not so anaerobic. You get more oxygen into the wetland when you have a planted wetland like this one. Now, about the efficiency, the treatment efficiency of these wetlands is very high, actually, as long as you dimension these wetlands correctly. You can get very high removal rates. For example, 98% here as an average of BOD5 reduction. So we can reduce 98% of the organic load coming into the wetland. Now, these efficiencies here are actually for the entire plant, including the Imhoff tank plus the wetland, right? So in the lines in the graph here, you can see the work that is being done by the Imhoff tank to the center of the graph, and then the second part is the work being done by the wetland itself. So as you can see, very high removal rates for BOD, COD, and total suspended solids, and less efficient rates for nitrogen and phosphorus removal. Although when you have a planted constructed wetland, then you get these numbers. If we didn't have plants, then we will come out of the plant with the higher levels of nitrogen and phosphorus. So the plants themselves are taking up some of the nitrogen and phosphorus contained in the water. Now, finally, E. coli removal rate is 99%, which sounds very high, but it's usually 99% removal rate of E. coli is usually not enough to have a totally safe effluent. So we will, even though we're removing 99% of E. coli, we will end up with some E. coli still left in the effluent, as we can see in this table. So this table is to compare the absolute values, the concentrations of the wastewater at the inlet and at the outlet of the plant. And on the last column on the rightmost column, we can see the control value in Nicaragua, to which we have to compare the effluent quality, right? So for example, conductivity, we should leave the treatment plant below 2,000 of conductivity. And on average, this plant was removing salts to 546, so it complies, right? And as you can see, all the measurements, all these parameters comply with the norm. Now, this standard in Nicaragua is for general discharge and for reuse when you discharge the treated water to the ground, right? If we were to discharge to a lake, for example, then these parameters will be much more strict. For example, instead of having a control parameter of 120 milligrams per liter of BOD, if we were to discharge to a lake, maybe this would go down to the 20 or 30 milligrams per liter, much more strict limits in order to prevent pollution to lakes. Eutrophication, as we have seen before in previous sessions. And now here, the E. coli, as I mentioned before, there's a very efficient removal rate. We're going from 1.6 times 10 to the 7th power to 7 times 10 to the 4th power. So there's a 3-log reduction already here going on. Nevertheless, the final effluent is 1.0 times 10 to the 3rd power, which this means 10,000 units of E. coli. No, I mean 7.0 times 10 to the 4th power, and the limit is to the 3rd power. So we still have to go 1 more log in order to leave the plant within the control value. What's the consequence of this? That if we have over 1,000 units of E. coli at the outlet, then we cannot use unrestricted irrigation, because if we irrigate lettuces, for example, with 10,000 units of E. coli, then we have the risk of having disease and bacteria in that effluent. So either we go 1 more step and we disinfect the water. We can use ozone, we can use ultraviolet light or chlorine or a sand filter, a green sand filter, if we have enough space. Then in that case, we could treat the water to a level in which it won't need restricted irrigation, and we could irrigate everything. In this case, there's no disinfection phase in this plant, so we have to irrigate specific crops that will be safe to irrigate with this type of water. And finally, Helmin X is not a problem here. We enter the plant with 23 units per 1,000 ml, and we leave the plant with less than 1 on average, so there's no problem there. The only parameter that we have to be concerned about in this case is the E. coli. And here you can see some pictures of the crops being irrigated with the effluent. They have tried and analyzed all kinds of different crops that grow below the surface, such as onion or cassava or peanuts, crops that grow in contact with the soil, like cucumber, crops that grow close to the ground, such as tomato or beans, and crops that grow removed from the ground, such as papaya. And what they have measured is the degree of contamination of all these different crops which were in contact with the treated wastewater. And here are some lessons learned from this case. First of all, plants take advantage of the nutrients, nitrogen and phosphorus, which are present in the effluent. No additional fertilizer was used in this case, so all the crops took the nutrients from the wastewater and, of course, from the soil. We can see the conservation of water resources here. The reuse of water reduces the pressure on surface water sources, also on treated water. In many countries in the Caribbean region, there's desalination plants which use a lot of energy, and you end up with very expensive water, right? So it's much cheaper to irrigate with this type of water, or any wastewater you reuse for irrigation will reduce pressure on these other expensive water sources. Also, the water flow in a treatment plant, especially if this flow comes from wastewater from a bunch of houses or a small population, is very reliable and stable during the year, right? So this allows farmers to produce all throughout the year when you have the weather, appropriate weather conditions. But the flow is very steady, so the water offer is very stable. And finally, crops should be selected based on the quality of the wastewater and the possibility or not of disinfecting the effluent. So this is where we use this multi-barrier approach that is recommended by the World Health Organization. So the crops which are recommended for restricted irrigation, this is when you don't have a disinfection step, are vegetables, fruits, and basic grains that are washed, peeled, or cooked before consumption, industrial crops that are subject to drying, roasting, or extraction processes, and fruit trees, and also tall stem plants and forage for animals, right? All these crops are appropriate for wastewater reuse for irrigation when you don't have a disinfection step. In the presentation, at the end, you will have access to these links. And of course, they will be uploaded to the resources section of the Crew Academy. And as I mentioned before, this is a very well documented case, and so you can go into these links and look at the detailed monitoring process of these plants, the removal efficiencies, the difference between the crops, and all this. So, right, this was the first case from Nicaragua. Very appropriate technology for tropical climates, the constructed wetlands. Next, we will look into an NGO project. This NGO is called Soil in Haiti. They have worked since year 2009 in Haiti. Soil means sustainable, organic, integrated livelihoods. Very, very sustainable ecological approach. In this case, they base their operation on urine diverting toilets. And the challenge they faced was to provide sustainable sanitation at very low cost where there were no sewer networks. And they worked all through the earthquake also in Haiti. So this also works as an emergency technology. So I mentioned the urine diverting toilets. You can see one in the picture on the right. The feces go into the greater hole in the back, and the urine goes through a pipe to it can go to a sealed container that can be then removed or picked up, or it can be also infiltrated into the ground, depending on the conditions of the place. In this case, what Soil does is they provide one of these toilets to a household, and then the household has to pay between $4 and $5 per month for the service of Soil to come periodically to the house and remove the feces and the urine. So as you can see, there's a plastic container on the left. So in that container, you have some sawdust. So after defecating in the toilet, you just pick up with a small cup some sawdust from the bucket and put it on top of the feces. So that starts a composting process. It absorbs all the bad odors, and you have some on-site composting process going on within the toilet. And there's another bucket within the toilet that has to be periodically removed. But interestingly enough, when you separate urine from the feces, you don't have bad smell problems, because the problem is when you mix the feces and the urine, then you have a very, very liquid effluent, and then all the ammonia from the urine especially starts smelling very bad. So as long as you infiltrate the urine or you lead it towards a closed container and you have some sawdust on top of the feces, then you don't have any problem of bad odors or flies or that kind of problem. The first composting station built by Soil took place in 2009. So Soil has carts and trucks to pick up the sludge from the households, and then they take this to a composting station. First, all the excreta plus the compost is placed in wooden boxes for a 2 or 3 month period. This is where the compost continues going on. And then after that, this is transferred to composting piles for about 6 months. Each composting station processes more than 50 tons per month. So while the composting process takes place, the temperature goes up close to 50 or 60 degrees. So all the material gets also disinfected because of the high temperatures. Here are some numbers on the main investment costs of this type of system. The composting plant itself costs about 150,000 US dollars. The trucks were around $25,000, and the carts, small carts, around 200 US dollars. So small carts do the collection from each household to a centralized place, and then from that centralized station, the big truck takes to the composting station. There's a very large, important impact reached by this project. Currently, there's about 6,500 people currently using this service and then paying for the service. Over 500 tons of waste are processed every year in the composting plants. There are education campaigns taking place and reaching over 1,000 people per year. And compost is also currently being sold to farmers. And you can see a picture of the type of bag of the compost. They have named this compost Lacay, and that's their brand, and that's how they are selling this to the farmers for improving their land as a fertilizer or as a soil improvement compost. The challenges they face is to improve the efficiency of all their processes, and they are considering subcontracting some of the activities so they can gain efficiency. Now we can take a look at a very short video from them, from Soil, and this is Sasha Kramer, the founder of Soil in Haiti.
In Haiti, over 99% of human waste goes untreated, with devastating consequences for both the environment and public health. In 2006, I co-founded Soil with a mission to really simultaneously solve the problems of poor sanitation and declining soil fertility by closing the nutrient cycle and using the nutrients from human waste to restore soil fertility. So what we do at Soil is that we've designed a small portable household toilet, which people rent for about $4 to $5 US per month per family. And the toilet has a 5-gallon bucket in it, filled with a carbon material that's used for flushing. And once the bucket is full, we take it away to our compost site where it is treated and transformed. It's a very simple process in which we just dump the waste into a bin, and then we step back and we let the soil microbes do their work. And when there's so many of them in there, it actually heats up the waste to a really high temperature, which kills all of the pathogens that make people ill. And in 6 to 9 months, we have an amazing finished product that can go back onto farms to restore soil fertility without having to rely on chemical fertilizers, which take a tremendous amount of fossil fuel to produce. Soil started our household toilet program, which is called Eco Lakai, in 2013. And we currently have about 5,000 people using our household EcoSan toilets. And from these families, we're treating 30 tons of human waste every month and producing between 5 and 10 tons of compost that we can then sell at the compost site.
Dans zone avoisinante tout, jeune en pile monde ta comme surtout qui gagne caillou ou construire ou pas gagne toilette. Et les comme ça yo même c'est aller dans la mer, aller dans base caillou cap construire yo, faire 2 jours dans sachet et puis voyer ailleurs. Ça distribue maladie, pas malade, la caille pas malade. Mais l'aime fin fait tout ça, eh ben on connaît on gagne de l'eau dans réserve, me laver même et puis on couvrir et puis la paix.
Soil's work is to really create a sustainable business model for sanitation provision in dense, informal urban settlements. And the way that the business model works is that people pay a small monthly fee for this toilet. So they don't pay the cost of the toilet. They actually rent it, and they pay for it on a monthly basis. And this fee covers the production of the toilet, the collection of the waste, and the transport to the treatment site. And then at the treatment site, because we're not only treating the waste, we're also transforming it into a valuable resource. It means that we can generate revenues to cover waste treatment costs through the sale of compost. Our vision at Soil is that in 10 years, it will no longer be Soil that's operating this program, but that the research and development work that we've done will have been picked up by private entrepreneurs and communities, not only in Haiti, but around the world where solutions like this are needed, and that these entrepreneurs will actually be able to make a sustainable livelihood, providing dignified sanitation to people who need it, but also to re-envision the way that we do agriculture.
Right, so that was the soil case in Haiti, and also you have more links in the resources section to learn more about this case. Let's move on with the other 2 cases. I would like to invite Selene Tripp from Borda. Please, Selene, if you like to present yourself and share with us the very interesting case from Nicaragua. Welcome.
Thank you very much, Gustavo. I will share my screen. Yeah, thank you. Let me know whenever you start looking at the presentation.
Yes, we are.
Okay, thanks.
You can put it in presentation mode,
yeah.
But it's looking right.
Is it in presentation mode already?
Yeah. Not yet. In the bottom, you have to click.
You see it now?
Not yet.
No.
There you go. Now you
do?
Yep.
Okay, so my name is Selene Tripp. I'm a project coordinator for Borda, Mexico. I live in Mexico City most of the time, but we have projects in different countries and also different areas within the different countries where we work. So I'm gonna present the project Integrated Management of Wastewater and Organic Waste for the Municipal Slaughterhouse of León, Nicaragua. I will go a bit through the general information of the slaughterhouse, the pre-intervention conditions, the strategic planning and the execution of the project, the outcomes, benefits, and the impacts that we have, and also the lessons learned. A bit of the general information. The slaughterhouse from Nicaragua is a public property which was built in 1966 for the slaughter of cattle and swine for human consumption. Currently, 140 cows and 120 pigs are butchered weekly, and it works with a staff of 17 employees, including technical, operative, and security members that currently work there. And the greatest characteristic of this place, and the reason I'm here, is that it has a wastewater and solid waste treatment system, and the end products are used within the premises in an organic orchard and also for sale. So a bit of the pre-intervention characteristics. The slaughterhouse initially was built outside the city, and it generated 60 cubic meters per day of untreated water, which was loaded with solid organic matter and was disposed in the discharge in a nearby river. However, with population growth and urbanization, it became part of the urban area, and all these poorly managed situation of all the wastewater became a rising problem because the neighbors began to complain about the bad smell, also complain about all the sewer clogging, and also began to realize the pollution of the river nearby. So there was a huge social pressure that urged for an improvement of the wastewater treatment system of the slaughterhouse. Also, there was a lack of vision regarding the solid and organic waste management. There were 1 to 1.5 tons of solid organic waste generated every day, and this was all disposed in an uncovered municipal landfill. Also, the workers were dealing with all this waste directly and also with very limited personal protection equipment. The premises where this slaughterhouse is used to have this vacant lot of 1,200 square meters, which was in disuse, and we decided that this was a space that needed to be used for a better purpose. So for the strategic plan and the execution of the project, this was initiated by the municipality and also the management department of the slaughterhouse. They knew of all this social pressure urging for an improvement of how they were dealing with all this waste. So they reached for some counsel and some advice to the cooperation programs where they participated. So this is how they got to Borda through the Hamburg City Twinning Project. And also we included the university as part of the stakeholders contributing to this project. All the stakeholders together worked on developing a strategic approach for a comprehensive solution of the problem. So this solution needed to be based on three premises. The first was that the solution needed to be long-term and sustainability of the project, meaning that it couldn't be just a quick solution. It needed to be well thought and well planned in order to take into account all the specific characteristics of the project and therefore develop the best solution. Also, we needed to simplify the wastewater and the solid waste treatment process and turn it to added value products. And we also looked for providing a better service through the continuous improvement. Before building anything or designing anything, we needed to have a better understanding of the effluent water. So we conducted an analysis where all the different areas of the slaughterhouse were analyzed and took into account because of the different characteristics that it brings to the effluent, from the slaughter waste, the cleaning of the slaughter cells, the cleansing of the guts, the leather and the skin processing, and the guts and belly, which includes washing the manure. The total amount of wastewater is of 40 to 60 cubic meters per day. And also what we got from this analysis is that blood was the highest pollutant with a total COD of 375,000 milligrams per liter, followed by livestock manure, which was the second highest pollutant because of its contributions to the total dissolved solids in the wastewater. Okay, after we had this idea of the wastewater that we were getting, we designed and implemented this system, which at the beginning, originally, it was working with one biodigester, where the biogas was contained in order to further reuse as part of the processes of the slaughtering. And all the solids from the biogas were took into a drying bed, while the water went into a baffled reactor, an anaerobic filter, which also had a containment for the biogas that was generated, also for further reuse. Then the water was led into a horizontal planted gravel filter, a tank, and then for reuse in irrigation of the crops of the orchard that we also built in that big land that I told you about before. So the project was running like this for a bit, but we soon realized of the importance of this sustained improvement method, where we need to plan, implement, but also very importantly to verify, identify any problems or issues and take corrective measures. In this case, one of the first issues that we noted was the rapid formation of the floating sludge layers in the anaerobic reactor. This because of the huge amount of organic matter coming, and because of the fact that we only had one biodigester. So this is where we can realize the importance of the design, but also of this analysis through the pilot projects and also adjusting to improve the performance of the systems. So that's how we got to conduct these adjustments, these improvements of the system. We added separated wastewater flows so we can have different first treatment systems for each of the areas of the slaughtering. We also added a screen for greater retain of the solids, grease trap also, and we added 2 more biodigesters so we can improve the capacity of our first treatment. The biogas again was contained and used afterwards as part of the processes in the slaughterhouse. We kept our anaerobic baffle reactors, anaerobic filters with the containment of the biogas. We needed to make some changes in the filter gravel, filter gravel. So the problem here was that we were getting a lot of sludge still in the artificial wetland, so we need to make some changes there also, because it was getting clogged still with all the grease from the blood. So we also made some changes there. We added some power pumps for the irrigation system and also a biogas incinerator, which is also needed as part of the slaughter processes. So we added this sun power pumping system, which took the water from a tank to an elevated tank powered with solar pumps, and then it was led to the orchard and used by a drip irrigation system. This is a diagram of how the reuse system is working now. So after the treatment with the different steps that I already mentioned, the water goes into the artificial wetland and to the elevated tank, and afterwards it's being released in the seed beds of the orchard by a drip irrigation system. And this is important because we don't put any water over the plants directly, but over the soil. And for the organic solid waste, we have this compost yard where we take the sludge that went to the drying beds, from the biodigesters to the drying beds. Then it's taken into the compost yard. It goes into a vermicomposting system, also a storage room, and also a shredder. The shredder allows us to manage better the compost and also take it into sale and also use in the orchard. So this project was developed and implemented through different phases since 2013 till 2020, and it's still running. And the total investment only for the construction was of about $190,000 US dollars. Some of the outcomes and benefits, impacts of this project, well, the most important one, I think, is that 16,000 cubic meters of water it's being treated every year. This is water that now it's not either going untreated into the river or better off, it's being reused for the irrigation system and also for irrigating the compost when needed. And the rest of it, that it's not being used in the orchard. In the orchard, we use about 35% of the wastewater that it's being generated because the water is too much for being reused. Also, some part of it, 65%, more or less, goes into the sewer system, but now it's completely treated and in compliance with all the industrial wastewater discharge parameters for Nicaragua. We are also reducing the environment pollution and also the bad smell that the neighbors were complaining about. For the solid waste management, 400 tons of organic waste are being transformed into compost every year. This compost can be used in the orchard, but also it goes into sale. And in this way, we are reducing the amount of waste that was going into the landfill. Now there's no waste, no solid waste going into any landfill, and it's all being reused for either the production of vegetables or for sale. Another benefit of the system is the biogas production, which is about 3,500 cubic meters of biogas per year, which is again also reused in the slaughtering processes, representing a cutback of 5,500 kilograms per year of firewood that was used to heat the water. And also now we have the biogas incinerator that it's also hugely needed in this kind of infrastructure. Again, some of the positive impacts is that we are improving the health and the working conditions in the slaughterhouse and also reducing some of the greenhouse gas emissions. And well, the bonus is that with the sales of the different crops and the compost, we are getting about $7,000 per year, which it doesn't mean that our aim was to recover all the investment only with the incomes of the organic products. It is like a plus with this kind of projects that we can generate some product that we can sell and also help the management and the running of the slaughterhouse with this income. Some of our lessons learned through this project is that, well, with the local government, it's getting highly engaged with the achievement of this project, and it keeps interested in maintaining and sustaining this kind of projects. We work with an interdisciplinary team building approach, which also meant building the strategic alliance and the involvement of the different stakeholders, including the universities. We came up with an integrated solution with an ideal vision of adapting to the current situation and the current needs. Well, we also learned that not everything comes out as planned, but it's very important to analyze why it didn't work and what we can do about it. We also consider important to anticipate some budget for any adjustments needed within the process in order to ensure a successful project and also improving the performing of the systems. Also, it's very important to provide a monitoring system that ensures the long-term operation and maintenance, and to adapt the technical solutions to the capacities of those in charge of the operation and maintenance, mostly the local capacities of the ones that are going to be responsible of these activities. And last but not least, the human factor. It's a very important factor in this kind of projects. It's not all about the technology itself. It's also about these interdisciplinary teams that work together for developing the best solutions, taking into account also the local capacities, and in order to conduct and to perform a better project along all the project phases. So that's our experience with the slaughterhouse in Nicaragua. Thank you very much.
Thank you, Solen. Thanks for sharing this very interesting experience with us, and also for keeping up with the time. 17 minutes, perfect. Turning waste into resources and circular economy, this is what this case is about. A project so important and necessary for everywhere in which we have slaughterhouse effluent with lots and loads of organic matter. Next, we have our second guest, Mr. Anthony Headley. Welcome, Mr. Headley. Please, if you could share your screen. Happy to have you with us with a very interesting case from Barbados. I'm sure we will learn about from this case. The floor is yours.
Good morning, everyone, and thank you all for this opportunity. Unfortunately, my camera is malfunctioning today, so I do apologize. This morning's presentation will look at the development of the water reuse policy for Barbados, and we'll just cite a couple examples in terms of water reuse within Barbados. Could you confirm that you are seeing the screen?
Yes, sir. Perfect. And anybody, if participants want to ask questions about any of the previous case studies, please type them on the chat box and we'll be answering as we go along. Go ahead, Mr. Headley.
Thank you. Just a brief on the presenters. So my name is Anthony Headley. As indicated, I'm the Director of the Environmental Protection Department, responsible for pollution control. And Dr. Mwanza is the Technical Advisor to the Barbados Water Authority's Board. And both individuals have in excess of 20 years experience in the field. In terms of the presentation format, we're just going to look at the context with respect to why we were in Barbados looking at water reuse, the approach that was taken and the existing laws, and just a brief on the current policy that was approved back in 2018, and then a couple case studies in terms of water reuse in Barbados. Why are we interested in wastewater reuse? Over the years, Barbados has seen some significant impacts on our marine environment, such that in several areas along the coastline, the coral cover has actually dropped significantly to around 24% coverage in some areas. Our studies have indicated that this is primarily caused either by human waste in terms of waste disposal, sewage, and agriculture as the two main areas of impact. And generally, the corals have the impact from groundwater discharges. So the figures that you're seeing are just changes in population density over the years up to 2015. And the second figures below is based on some modeling showing the different scenarios looking at adjustments either in wastewater treatment within the area of breakdown and changes upstream of breakdown in terms of agricultural inputs. So the land use component was a very significant, or is a very significant component. and drought issues for Barbados as well, where we have seen over the years several periods of drought that have driven to some extent this process and pushed the need to start looking at all sources of water that is available to us. Another driver in terms of water reuse is that several facilities in Barbados have actually, based on the availability of water and the cost of water, noting that all of our water for domestic purposes is taken from groundwater sources, which involves pumping from the groundwater aquifers, which is very expensive because of the cost of electricity in Barbados. So we've seen within the hotel sector, residential sector, and primarily based on the advocacy of both the EPD, Ministry of Health, and the water authorities between 95 and 2010. Because of that advocacy, several facilities actually started putting in wastewater treatment systems and using some of that wastewater for reuse in terms of irrigation. The primary tool that was used would have been the health services building regulations for control, and the main condition was utilization of drip irrigation systems. So a lot of facilities that undertake wastewater reuse have done so generally without a formal system of standards, as well as a system of monitoring. Some of the government facilities that have installed wastewater treatment systems or rainwater systems and have looked at wastewater reuse are highlighted here. And the one that we will be looking at today will be Harrison's Cave, which is a special area in Barbados that's fairly important to our tourism sector. These are the legislative tools, and as I indicated, the Health Services Building Regulations and the Town Planning Act would have been the primary tools used to control water reuse in those initial stages, still being used as we speak. But unfortunately, they do not address all of the issues that are associated with water reuse, and particularly some of the health concerns. Supporting those regulations would have been the existing groundwater protection policy, which is the diagram on the left, and that has been updated in 2020 to the diagram that you're seeing on the right. Historically, when looking at the diagram on the left, the gray area along the coast, there are no restrictions with respect to waste disposal. This was classified as Zone 5, and disposal would occur from the residential property directly into what we would call a suck well, untreated, where primarily treatment of waste would have occurred in the ground, either through filtration and natural biological processes. So some of the primary drivers towards the wastewater reuse policy would have been public health, given that it was being practiced within the country, and there were concerns with respect to cross connections, particularly between those facilities that did wastewater treatment and connections to the potable water supply system on property. No structured legal institutional framework specifically looking at all the areas to ensure safety of wastewater reuse. Then the other driver would have been the Cartagena Convention and meeting the requirements under the Cartagena Convention, and generally to augment the water supply within Barbados. So if we can use available water, have it treated to an acceptable quality, then domestic potable water that is expensive, we don't necessarily need to use that, which is of very high quality for all the purposes that we use water for. So those were the drivers behind the development of the water reuse policy. The approach that was taken with respect to this policy was that a consultant was hired back in 2005, and that consultant basically was given the mandate to update the West Coast Storage Project Master Plan and to do a cost-benefit analysis on that plan and look at the different options that were available to us. This was done through a technical review. We had 3 stakeholder consultations, extensive consultations with a variety of players in the field, including the architects, the engineers, and the farmers. The output of that particular study, and as you can note the dates, the draft water reuse was in 2006, and the cost benefit analysis looking at the different options in terms of water reuse was in 2008. I'm getting some feedback. Okay, thank you. Coming out of that study, and I just would mention some of the challenges here during the development. A number of administration changes occurred, and after each change of the administration or change in the government, we had to set out afresh the case. So when the report in 2008, the consultancy was finished, within a couple of months, there was a change in the administration, and it took about 3 years after that change in administration before we got back on stream in terms of the development. Through a technical committee, we then were requested to prepare the policy around 2012, 2013, and these were the 3 departments: the EPD, Environmental Protection Department, Water Authorities, Health, and Town Planning Department. We also took the opportunity to review the historical work under the first JEF project, and that culminated in the institutional and legislative reform review. And after that, we had completed the water reuse policy. What is the policy? The policy is basically set out with a vision and 3 main objectives. The vision basically looks at, we're trying to change the culture with respect to water to ensure that water is viewed as a national resource, and that all forms of water need to be used for national development. So we're not viewing water as necessarily a waste, but as something that can be tapped into to ensure that we maintain our national development in a sustainable way in green economy approaches. We're going to do that with 3 main objectives: ensuring the safety of the water, looking at and having the appropriate guidelines for reuse, and ensuring that this information is communicated in an effective manner to all of the stakeholders. The current institutional arrangements as we continue to plan is highlighted here. This was presented back in presentation 4, so I wouldn't spend much time on that, so that we can turn quickly to the case studies. As indicated, the Harson's Cave area, and I've chosen 2 examples within the Harson's Cave area. The Natural Heritage Department was actually the project unit responsible for the rehabilitation of the Harson's Cave. And the work that was done was really and truly based on some work that was done by Dr. Mwanza, looking at the hydrology of the area and the impacts that we were seeing on Harson's Cave. So this small treatment plant was put in place for the Natural Heritage Department, which has about 7 permanent staff. At the time when it was installed, there were about 20 transient staff and 3 to 7 consultants at any point in time. The department was very active in the community, as part of the overall national project was not just the rehabilitation of the Harson's Cave area, but to encourage more participation of the community to ensure sustainable livelihoods. The property in question is approximately 4 acres, and the area is designated as a zone of special environmental control under the planning, physical development planning order. Overall, nationally, we're looking at different types of systems. As we've indicated, Barbados is a small country, and one of the challenges that we have is we don't have a lot of land space for different types of treatments. And we also have a challenge in terms of the cost of the different treatment systems. So one of the systems that was considered at the time was a Chroma Glass 5 system, small package treatment plant. And for those who were around back in 1990 to 1993, the PAHO work that was done, which was a survey on the hotels within the Caribbean, had highlighted some traditional challenges dealing with package treatment plants. And what we've sought to do over the years is to address some of those challenges that were identified within the PAHO study published in 1993. That was the issue of the persons who are maintaining the treatment system and the level of investment in terms of operation and maintenance of those treatment systems. This particular plant cost around $31,073 to install back in 1999. And one of the conditions of approval, in addition to the issue of drip irrigation, looking at public health, was to ensure that there was a maintenance contract. So government was basically demonstrating to the private sector through this particular project for those who had the capabilities of installing plants, the appropriate approach or our preferred approach to wastewater treatment. And as indicated, this is a standard treatment system with grit screening, a chamber for holding the sewage and aerating the sewage. The sludge generated from the first chamber is actually pumped on a periodic basis, and that is taken to the Barbados Water Authority's main treatment plant, which is then further processed and discharged, trucked to a site at Spencer's, and then the effluent is disinfected with some chlorine, and via gravity, when you see the picture, as this picture here indicates, this is the treatment plant. And as you can see from this picture, the grounds slope naturally. So by gravity, the drip irrigation system was distributed throughout the property for irrigating the variety of plants that were used on the property. Ironically, however, this particular area in Barbados is a very high rainfall area, and when I spoke to the operator yesterday, the drip irrigation system is no longer in operation. That was discontinued. So these are the technical specs of the package treatment system. The initial chamber provides the holding for solids, the inorganic solids. The second chamber provides for the aeration, and the baffle, as indicated here, is a perforated baffle that allows continuous connection between the two, and the final clarification chamber. So it's basically a batch operation, 6 to 8 hours treatment times prior to clarification and discharge of the effluent. The standards that were used, and from our initial monitoring during the commissioning and the first few months of monitoring of the treatment system, indicated that it certainly did comply with the standards that were set under the conditions of approval. Our challenge now in terms of monitoring these systems is generally the laboratory capacity in Barbados for evaluating the performance efficiencies of the plants. The lab had indicated for quite some time, due to the significant cutback in staff, that they were not capable of doing the continuous assessments that we require for all of the treatment plants that we currently have on island. Right. Our second case study is again the Harson's Cave. Specifically, this is the #1 national tourist attraction. It's located as similar to the Natural Heritage Department within the zone of special environmental interest. We have, during the high days, as much as 179,000 persons visiting annually. That is at a low now of around 100,000 persons since 2013, and because of the coronavirus and the impacts of the coronavirus, the visitor numbers are certainly down significantly. But these were the drivers for some of the drivers for the installation of the package treatment plant. The property is really a small property, and part of the reason as well was that the cave, though very spectacular, was having some significant impacts from pollution in terms of tarnishing of the stalactites and stalagmites. On some days, there were odors generated from water that was entering the cave, and hence government needed to start looking at solutions. So the Natural Heritage, being the project manager for the Harson's Cave project, was demonstrating the importance of wastewater treatment and improving the quality of the water that was entering the cave from the developments above the cave as well as the developments surrounding the cave. A second part of the impact would have been agriculture. A decision was taken, given the size of the property, again, to look at a package treatment system. And in this case, persons were very concerned about the quality of the water entering the cave, particularly from the study that was done by Dr. Mwanza and the impacts that we're seeing there. For those who have actually visited Harson's Cave, the cave is within, the entrance to the cave is an artificial entrance that was created within the cliff face. So it's a 2-level type system. One level, so there's one treatment plant and a second treatment plant at different levels within the plant. And because we wanted to have high quality effluent, ultrafiltration systems were chosen. So the ZWEED 508 membrane bioreactor was chosen. These are typical examples of the layout. The structure on the right is actually located on the top of the treatment plant system, which are the controls. And the irrigation water, the reclaimed water, is used to irrigate all of the plants on the property. And drawing here on the right just shows the different arrangements in terms of the process flow. So there's the trash chamber, the equalization tank, given the significant, in any day, there's a significant change in the number of persons visiting Harson's Cave. It was thought that an equalization chamber, in terms of stabilization, the flows going to the aeration chamber, was very necessary. Hence, an equalization tank was installed to control the flows. As indicated, this was part of the multi-million-dollar project. I wasn't able to get the specific cost for this, but from other systems in Barbados, the range could be between 800,000 Barbados dollars to 1.2 million. Similar to the Natural Heritage Department, we had insisted as the regulatory agency on the company who manages Harson's Cave having a maintenance contract. And that is one of the benefits that we've seen throughout the years in terms of the use of the conditions of approval. We have now at least 4 different companies that are involved in wastewater treatment. Prior to 2000, there were no companies outside of the Barbados Water Authorities that were involved in the maintenance of wastewater treatment systems. Now there are at least 3 companies that import, install, and manage package treatment systems on behalf of their clients, which we believe is a plus in terms of wastewater reuse and wastewater treatment. For this particular one, the standard that was used was a little bit more rigid standard. When you look at the BOD and totally suspended solids and the total nitrogen, this was coming out of the marine pollution study. I am going over time, so I would go through quickly the latter part of the presentation. This is going forward. This is what is being planned. We are planning an update of the South Coast Sewage Treatment Plant. The capital cost for that plant is approximately $105 million. It would include an 18-kilometer pipeline to transfer water from the treatment plant on the south coast to the east of the island to a place known as River Plantation, which is a large area for farming, and the main limitation is the availability of water. Important component just to note is the addition of the reverse osmosis section on the plant on the back end. This is designed, is going to be designed to reduce the total suspended solids to around 450, which is the mark identified within the FAO standards for water. When we did a cost-benefit analysis in terms of the agricultural use of the effluent, given the high capex costs, we showed that the water or the cost could be 1.58 Barbados dollars. And if we make adjustments to an economic instrument that we are currently using, a sewage and garbage surcharge on the water bill, that cost can actually come down to 63 Barbados cents when spread across the entire island. Another benefit coming out of this South Coast is a review of the standards, and we've now have 2 sets of standards, one for potable water discharge into the potable water aquifer and a non-potable water aquifer. And these are the standards here. Given that I am out of time, I will stop here, and certainly the presentation would be made available to the participants. But quickly, what will happen at the end of this entire process is we expect to have a Water Reuse Act and regulation. In terms of the health concerns, we're having the Barbados National Standard Institute work on a dual, updating the current plumbing code to a dual plumbing code so that there are clear standards for all persons involved in terms of the color codes for the pipes used for reclaimed water, potable water, etc. And under the current Crew Plus project, we're going to be preparing the communication packages to ensure that we engage all of the stakeholders appropriately with respect to wastewater reuse. And finally, we're looking at establishing the wastewater reuse revolving fund. That assessment is also being funded by the Jeff Crew project. Thank you very much.
Thank you, Mr. Headley. Thank you for your great presentation. Just to remind everyone that all presentations are in the link. I just pasted to the chat box. There were also some cases in the Spanish language sessions that were not translated to English, but you can still access all the materials from the Spanish sessions as well. So I will share the link for all the materials also on the screen. And having said that, I will invite Mr. Chris Corbin, who wants to share some closing remarks with us in this final session.
Thank you very much, Gustavo. I know time is tight, but there was an interesting question. I'm wondering if Mr. Headley could take a quick look at and try to maybe not respond in full detail, but this has been an issue that has come up in other discussions about the efficiency in removing of nutrients and whether or not there's need to add other types of polishing systems. So I wondered if he could just quickly look at the question in the chat and see if he wants to give a very quick response, but perhaps then maybe type in something a little bit more detailed before I sort of go into just some final remarks. Thank you.
Okay. Thank you, Chris. Just a quick response. Yes, the chromoglass system, in this case, the sludge generated in the first tank, the inorganics, that is taken to the Barbados Water Authorities. Most of our package treatment systems are like that. In terms of the treatment efficiency for nutrients, the treatment efficiency is not that great for nutrients, and certainly there can be some improvement. In this particular case, the system can have a denitrification option. It is based on the programming and the retention time. But that option was not used in this case as it was being used for irrigation. But the system has a programming option for denitrification. So that denitrification component was not tested. I would look at the rest of the question and respond in writing.
Okay, thank you. Thank you so much, Anthony. And again, yeah, I have a few minutes, and I guess the first thing I want to just say is congratulations to all of the participants who managed to stay with us through all of these courses that have been organized through the Crew Plus Academy and a joint initiative between GIZ and the UNEP Cartagena Convention Secretariat, the two of the three co-executing agencies for the Jeff Crew Plus project. I also just want to express my sincere appreciation to Gustavo, and I know it's not possible, and maybe there's somewhere that we can do a virtual clap, but Gustavo has been doing this now for, again, the last 6 weeks in both Spanish and English every week. He's been being the one I know following up with all of us to make sure that everything was on cue and all the presentations were ready. So Gustavo, sincere appreciations from all of us. It's been wonderful working with you, and your knowledge of the sector, I think, definitely came through with all of the participants. I'd also like to appreciate all of the presenters who have shared their own experiences, both in the Spanish-speaking session and also in the English-speaking session. Many of our partners, including the IDB, including UNEP, including other regional and global agencies, on this very, very topical issue. And we are particularly appreciative of the country representatives. We had Mr. Headley today sharing the experiences on what's possible within our specific countries, in the case of the Caribbean small islands, but also in the case of the Central American and South American countries that are taking part in Crew Plus. When we came up with the Crew Plus Academy, we weren't sure sort of what direction it would take. And we're really happy that the GIZ sort of, took the first baton in the organizing of the first phase. We were happy to learn from their experience and build on it in the second phase of the training and capacity building. And this is not the end. One of the major focus activities of the Jeff Crew Plus project is building capacity, providing avenues for exchange of best practices and lessons learned. And I think too often we have gone to Europe and North America and outside of the region when we have really excellent experiences in the region that we can learn from, we can replicate, we can adapt, and we can use to meet our own priorities and needs. So we have already been discussing what will the third phase of this Crew Plus Academy look like. This one was a little more formal in terms of being able to provide all of you as participants with formal certificates. We welcome your recommendations as to what are the types of training, where are the gaps, what should we be focusing on? How do we bring forward this issue of integrated water and wastewater management? How do we link with energy and pollution and human health and tourism? How do we partner more effectively with the private sector? And how do we get the sorts of technologies that Gustavo has shared with us? How do we get them adapted and used at a local level, at a national level, at a community level? I just wanted to maybe close. There are a number of other persons behind the scenes, both from the GIZ and UNEP, difficult to go through them all, but suffice to say that this has really been a team approach. It's been a pleasure working with many of my colleagues who have helped share the links, help provide the resources, in some cases sat in for me. David Wilk, who is our expert consultant you have met, and he has played a real leadership role in helping to convene these capacity building sessions along with Gustavo. And yes, the registration form is there. Please, I encourage people to complete the closing evaluation. But I also want to think of this group as a network that we continue to work with moving forward. We really want to hear your ideas. The project has a certain framework that it has to function, but it's also, we want the project to be responsive. We want at the end of Crew Plus that we leave a little bit of a legacy and a greater capacity to address this as an issue. So that would be me in terms of speaking on behalf of UNEP. I don't know if Gustavo or any colleagues have any other final remarks, final words, final thanks, but it's certainly been a pleasure. I haven't been able to be here for everything, but I'll be here for most of it. And yes, another exciting tool that we have coming up, we have also listened to you about knowing what technologies exist and what works and what can be adapted. And again, some excellent work that will be done through Border and the GIZ in terms of developing and finalizing a draft. So we, again, look forward to many of you, particularly those working with the different Crew Plus countries, to participate in this. But those would be my closing remarks. Gustavo, I don't know if I guess I really should hand back over to you as our lead trainer and facilitator, and anything else I might have missed. Thank you so much.
Thank you, Chris, for your kind words, and thank you everyone for being here, all 6 sessions. It's been a pleasure sharing with you all this course. Thanks again, and see you soon.